Primordial stars are one of the most interesting topics in astrophysics. We have never seen a primordial star, so the field is really driven almost entirely by theory, although at the end of my discussion I'll talk about some observational clues that we can get from looking at them. So the first issue is what is the difference, what are the key differences between primordial stars and the stars that are forming today? And there are two main differences. The first one is that primordial stars do not have any heavy elements. The heavy elements, such as the carbon, nitrogen, oxygen that we're made of, are all created in the interiors of stars. And we're now talking about the very first stars, so we haven't had a chance to make any heavy elements. So this means that you're talking about star formation that's occurring basically in hydrogen and helium. There's a very trace amount of lithium, but that's so small that it really doesn't have an effect. The second difference is that whereas star formation today occurs when the gas in the interstellar medium accumulates enough so that it can undergo gravitational collapse. In the very beginning, it turns out that the gas was actually fairly smoothly distributed, and it was in the dark matter, which has about 4 times more mass than the baryons do, that it was the gravitational potential wells in the dark matter that seeded the first stars. So the gas was fairly smooth, as I said, and that's because the radiation could freely travel through the gas up to very large scales. And certainly on the scales of stellar mass, then the radiation smoothed everything out. But the dark matter does not interact with radiation. And potential or fluctuations in the density of the dark matter grew from the initial time of the Big Bang and became nonlinear at redshifts of order 100 or so, and gas could then fall into these gravitational potential wells. So as the gas falls into the wells, initially the gravity is dominated by the dark matter, but then as the gas accumulates enough, eventually the gas does become self-gravitating, and it can fall deeper and deeper into the well and become eventually become a star. So as the gas contracts, it is cooled by trace amounts of molecular hydrogen that are produced in the gas. And when the gas gets dense enough, at densities above about 100 million particles per cubic centimeter, then it turns out that you can form molecular hydrogen by a 3-body process where you have 3 hydrogen atoms. So I'll try to do this with my fingers. I have 3 atoms coming together, and then they interact all together, and one of them flies away, taking away enough energy so the other 2 remain bound as a molecule. So above that density, the gas becomes molecular, and it then is able to cool effectively and continues to contract. A problem that then arises is whether this gas is going to undergo fragmentation. And this is something that is studied through numerical simulations. At the present time, it's not known exactly how this comes out. Some researchers find a great deal of fragmentation, others find less. So a key question is, what is the mass of a primordial star? And this is important for 2 reasons. First of all, if the primordial stars had a very broad distribution of masses, such as contemporary stars do, and in particular, if the primordial stars extended down to masses less than about 8/10 of the mass of the Sun, then such stars would be able to have survived all the way from the time that they were formed, shortly after the Big Bang, till today, and we could see them. We would actually be able to see a low-mass star that had no metals in it at all. And no such stars had been seen. So apparently they were more massive than that. It then becomes very important because you could say, well, if the stars are more mass than 8/10 of a solar mass, but less than about 8 solar masses, then they would have died and they would have left behind white dwarfs. And white dwarfs are very difficult to see because they're so faint, and they would have cooled off. So they would essentially have disappeared. But if they're more than about 8 times the solar mass, then they would have exploded as supernovae. And that becomes very important because depending on the mass of this primordial star, when it's large enough to produce a supernova, it can undergo various fates. For some range of masses, in fact, when it exhausts its nuclear fuel, the star just collapses into a black hole and nothing comes out. There are other ranges of mass where the star will undergo a supernova explosion and blow out all the heavy elements that it's created. In fact, there's a particular range of mass above about 140 solar masses in which the star explodes so catastrophically that there's no remnant left behind at all. All the material in the star is blown out into the surrounding intergalactic medium, and this is all in the form of heavy elements. So the mass of these first stars determines whether they're going to wind up being black holes, white dwarfs, and what elements are going to be injected into the surrounding medium. So what then determines the mass of one of the primordial stars? As I mentioned, these stars are forming in a very large dark matter halo, a deep potential well. The dark matter itself might have a mass of order 1 million solar masses, and it's accumulating gas. And the gas can overcome its internal support due to the thermal pressure when it has a mass of hundreds of solar masses. So you might imagine that the typical star would be of order hundreds of solar masses. So the star is trying to form, and as it forms, it initially starts off at a low mass, like the sun, and it then is producing radiation. As the star grows more and more massive, it produces more and more radiation, and furthermore, the temperature of the radiation goes up. So it's believed that the key thing that occurs is that the star will emit enough radiation that is ionizing the surrounding gas, that it will be able to then ionize and heat that gas to the point that it can no longer accrete onto the star, and that will determine the final mass of the star. So both analytic theory and numerical simulations suggest that you get a range of stars of masses, say, typically going from maybe 50 to several hundred solar masses. All these stars are large enough so that they can explode as supernovae. Some of them might leave black hole remnants, some will explode entirely. And it's a very active field of research then, is to try to understand exactly how these supernovae work, what are the effects of the rotation of the star and affecting the elements that are produced. How is it then that we can try to learn about this today? This all happened over 13 billion years ago. Well, there is an observational clue, and this field has been dubbed stellar archaeology, looking for very, very old stars, not the first stars that formed, since they formed with no heavy elements, but the second generation of stars. Those stars actually incorporated the heavy elements that were made by the first stars. And as I described, we can tell or infer what the mass of those first stars was from the pattern of heavy elements that are produced. So astronomers are doing very large surveys of hundreds of thousands of stars, looking for stars that have a very low metal abundance. And by metals, I mean not just metals in the way that we refer to them, but in astronomical lingo, that is stars, metals refer to just heavy elements in general. And astronomers have found that there are many stars that have, for example, iron that's 1,000 times less in these stars than the sun. They found some that have 10,000 times less, even more than 100,000 times less. And I think now there's even a claim that there's one that is more than 10 million times less than the iron in the sun. An interesting feature of these stars that is not fully understood yet is that even though they have this very, very low iron abundance, they do not have very low carbon abundances. So their carbon abundance is generally at least about a thousandth or maybe a 10,000th that of the sun. So that if you then look at the ratio of the carbon to the iron, then as you keep on going down and down in iron abundance, the ratio of the carbon to the iron gets larger and larger. And that is a very interesting clue as to the nature of these first stars. There are the large surveys will eventually be able to resolve this issue and determine, I think, fairly unambiguously what the nature of the first stars is.